Welcome to the Imaging Chain Basics video. My name is Kate and I'm a clinical educator working at Olympus OAZ. I've spent the last 12 years working within the hospital environment, primarily within nursing, education and support roles in the OR. So like yourselves, I understand that the abundance of devices used in the medical world can be overwhelming. This video is designed to help simplify the different devices used to generate the surgical image. So what is the Olympus imaging chain and how can it help you to understand the process of generating an endoscopic image? The Olympus imaging chain consists of 6 basic essential components: telescope, light guide and light source, camera head, processor, monitor, and cables. The better the quality of each of these components, the better the image that will result. A break in quality in any one of these components will lead to a loss of quality in the resulting image. A solid understanding of the imaging chain components is crucial to help you deliver an image that's of the best possible quality for your customers and patients. Advancing your understanding of the imaging chain can help you to work closely and consultatively with your customers, not only to troubleshoot when something goes wrong, but also to help optimize their experience in the OR. The key is in understanding that the image on your monitor is a direct result of several specific components or links, with each of these links performing a specific role in the imaging chain. Therefore, the image resulting from your imaging chain is only as good as its weakest link. The content of this video will be delivered from a surgical imaging perspective. However, the core concepts will be relevant across specialties. There are also a range of ancillary devices which can be used in conjunction with the imaging chain, but we will not discuss these in detail during this video. This video is focused upon the 6 essential components of the imaging chain. Let's now talk about each of these components and how they work together to generate the endoscopic image. For the first component of our chain, let's start at the patient end with the imaging instrument that comes into direct contact with our patient, the telescope. The telescope is the first component of our surgical imaging chain. A telescope is a tool that is used to observe an object from an appropriate distance and then relay the image to the observer in a practical way. The typical type of telescope used in laparoscopic surgery is a rod lens telescope, but there are also other types of scope used in the surgical realm, such as fibre optic and video scopes. Each has their own advantages and disadvantages. For more in-depth discussion on the different types of surgical scopes, please see the Olympus Imaging 3 Types of Scope video. Although surgical telescopes come in a wide variety of shapes and sizes depending on their application, the basic principle is the same: to gain visibility through a cavity in the least invasive manner possible. In surgery, that's through either a naturally existing orifice, such as the nose, airways, or looking into the bladder via the urethra, or this can be done through a small incision, such as into the abdomen in laparoscopy. The aim is to achieve the best possible view of the target tissue for either diagnostic or therapeutic purposes, whilst causing the least possible trauma to the surrounding tissue. Telescopes allow us to carry the surgical scene outside of its cavity and project it onto an ergonomically positioned surgical monitor. To maintain a high-quality image where no detail is lost, telescopes must be made from specialised glass lenses and fibre optics, which means they need careful handling. Furthermore, consider that the lens of the telescope is our surgical eye and it must be kept clean at all times. The different angles of these lenses allow us to adjust our surgical perspective according to the target tissue. Some common angulations used in surgery include 0 degrees or flat lens and 30 degrees. Aside from the different lens angles providing various directions of view, telescopes also come in a range of diameters, usually expressed in millimetres. Different diameters of telescopes allow for different sized optics to be used, depending on the diameter or the size of the passage or cavity which is being observed. For smaller cavities, such as shoulder joints or, for example, the bladder, a smaller diameter telescope will be required. Smaller diameter scopes produce a smaller sized image, for example, this 4mm telescope image. These smaller diameter telescope tubes are potentially less traumatic for patient tissue and more ergonomic for the operator working in a small space. For a large cavity, such as the abdominal cavity, a larger image may be required, usually through a 10mm or potentially 5mm telescope. This allows for larger optics and lenses to be used and can help generate a bigger, better quality image. But telescopes don't just relay the image, they also help us to deliver light into the cavity within which we're observing. This is crucial when working within the body. Light is delivered via a bundle of tiny fibre optic strands which run along the shaft or tube of the telescope. When using a rod lens or fibre optic scope, a light guide will also be required to carry the light into the telescope from the surgical light source. The connection of the light guide onto the telescope is a simple thread twist. However, if you're going to use a competitor telescope or light guide, you may need an adapter. Just see your system IFU. This leads me to the next component of the imaging chain, the light guide and light source. As mentioned, we need a light source in order to view delicate tissues within bodily cavities. At Olympus Surgical, we use a xenon bulb within a light source unit. Typically, the unit will be labelled with CLV for platform or generations such as 180 and 190. Olympus utilises xenon light because it's as close as possible to bright natural sunlight, unlike other light sources which can have a yellowy or blue tinge. Remember we mentioned the light guide that carries the light from the light source into the telescope? Well, these light guides are filled with around 40,000 tiny glass fibres, each carrying xenon light from the light source into the scope. Then light continues to travel along the telescope, illuminating the optics, and finally the light is emitted at the lens. Depending on the diameter of the telescope you are using, you may want to use a smaller or larger light guide. Olympus sells two sizes of light guide, small and medium. The smaller light guide is suited to smaller diameter telescopes, such as those used in urology with a 4mm diameter, and this smaller light bundle ensures that the light post of the telescope does not overheat and cause unnecessary heat-related wear to the telescope components. The operation of the light source itself is relatively easy. Simply plug in the light guide and power the system up. Once the surgical operator is ready, press the on button. It's important to note that to turn on an Olympus light source, it's just a quick press, whilst to turn off, you need a 2-second hold of the button. This is a safety feature that prevents the light from being accidentally turned off. In terms of adjusting the surgical light, it's recommended that the light source be set to auto with a baseline of around 0. If your light guides or telescopes are a bit old or you're in a very large or bloody cavity, you may want to increase your baseline of light delivery. You can increase your baseline light delivery by pressing the plus button and decrease by pressing the minus. The auto light function utilises communication between the light source to adjust light delivery according to the surgical site. That is, in the instance of flare or darkness, the processor communicates to the light source and light delivery is adjusted accordingly. This video has been slowed down to show how the processor and light source can communicate to adjust according to light requirements when set to auto. The actual adjustment happens so quickly it can't really be noticed by the system user. If the light source is set to a manual, then there will be no auto adjustment of the light according to the surgical site. So now that we have our telescope ready to deliver light and view the anatomy, how do we actually view the operative field? We could eyeball through this eyepiece here, which we call the ocular, but this isn't necessarily ergonomic nor conducive to maintaining a sterile operating field. What I want to do is digitize this image so that I can transmit it onto a monitor. That way my assistant, my scrub nurse, my anaesthetist, everybody in the room can see where the procedure is at and we can all work together for optimal patient care. This leads me to the third part of our imaging chain, the camera head. The camera head is responsible for receiving the image from the optics of the telescope and turning them into a digital image signal. This is typically done by a computer chip sitting behind the camera head lens. The chip receives the light or photons onto its surface. The chip then digitizes them, turning them into an electronic signal. Camera heads come in various shapes, sizes, and capabilities, depending on their intended use. Camera heads are ergonomically designed to sit in the operator's hand comfortably, whilst the electronic cable carries the signal back to the tower. This leads me to the next component of our imaging chain, the processor. The processor unit has electronics and software especially designed to understand the digital signal which it receives from the scope and camera head. The processor acts as the brains of the imaging chain, our central control unit. The processor allows us to make any necessary adjustments of the image, such as image storage, enhancement, or colour adjustment. The white balance is also performed on the processor, and the white balance is set by pressing the allocated button once you've connected your light source and turned on the light. The processor also allows us to turn the digital image into a signal that we can output and that we can display on the surgical monitor. There are a number of different signal types that can be put out by the processor, depending on which monitor you need to use or which cables you have available. As you can see from this setup, cabling is an important part of the basic imaging chain. Cabling allows all that electronic information within the processor to be output to other devices such as monitors, image management units, and printers. Cabling is a crucial part of the imaging chain, and there would be no digital surgical image without it. Depending on the type of setup you're using, cabling can be quite complex. Please refer to each IFU and to your local field service engineer for specific information on how to cable each unit. Of course, the easiest sign that you have your tower cabled correctly is to see the image on the screen. This brings me to the final piece of the imaging chain, the surgical monitor. A good surgical grade monitor will allow the whole surgical team to stay aware with how the case is progressing. Multiple monitors can be positioned to suit the environment and procedure. Surgical monitors simply display the surgical digital image which they receive from the processor via the cabling. Surgical monitors come in various models, but it's important to optimise your image by picking a monitor that's capable of a resolution and quality that suits the rest of your imaging chain. For example, if you're using a HD camera head, you want a processor and monitor that's compatible and capable of a HD image. Or if you're using a 4K processor, then you will need a compatible camera head and ideally a 4K monitor in order to get the most out of that 4K picture. Remember that the surgical image on your screen is only as good as the weakest link in your imaging chain. For example, you could have a 4K monitor, processor and camera head, but you could still jeopardise your image if you attach a poor quality, old or damaged telescope. In summary, you want to have the best possible quality for all 6 of the essential imaging chain components: the telescope, light source, camera head, processor, cables and monitor. I hope you found this video useful as an overview for the essential components of the Olympus imaging chain.